In the previous video, we worked through this simple example to illustrate the basic idea of arithmetic coding. And in this video, we're going to do another example. Now, I should mention that in both these examples, we are assuming a very simple probabilistic model of the source. Essentially, it's an IID model. And the way that that is manifested in the algorithm, as we've described it, is that at each step, we're subdividing in exactly the same way, and in a way that doesn't depend on the previous symbols. So we'll talk about later how you can modify this, and it's pretty straightforward actually, to modify this to handle very arbitrary models of the source. So I should also mention, I want to make a point of clarification here, which is that when we got to this point, where was it? This point right here, 1011, in this conceptual second part of the process, we had a number, 0.6875, that was contained in the interval from 0.68 to 0.712. And when we kept on subdividing to find a chunk that was contained in this interval, I chose the upper half. But you might have wondered why I didn't go with the lower half. You know, I could have kept subdividing this guy, 1010. And the reason why I did the upper half was because 0.6875 is closer to 0.68 than it is to 0.712. So I knew that by going with the upper half, it would take me no longer than if I had gone with the lower half, because I had more room to play with above. And this illustrates an important part of the encoding process, which is that you should choose the shortest possible binary sequence whose corresponding interval lies in the interval from A to B. It's not enough to just choose some arbitrary sequence that has an interval contained in that. And the reason why it's not enough to choose any old sequence whose interval lies in there is for reasons of unique decodability, in the sense of if you are concatenating multiple messages together, you want this code to be uniquely decodable. And I'll talk about that in more detail in another video. Why? So it's sort of to explain that distinction a little bit more clearly. You might have wondered, for example, along the same lines, the reason is the same. Along the same lines, why didn't we just use this sequence here, this 1011, to encode? That would be shorter, and that might even be better. And the reason that you need to go the full way to get the interval that lies in there, not just the number that lies in there, is if you want to have uniquely decodable code, in the sense of being able to decode multiple concatenated messages. If you don't care about that sort of unique decodability, then in fact you could just use the number. All right, so I'll talk about that more in another video, but let's now do another example. So this will be example number 2. So in example 2, let's say that our source alphabet, 0, is now, let's make it a little bit bigger. Let's add a 3. So we're going to have 4 symbols in our source alphabet, and let's take the convention now explicitly that 0 will be our end of file symbol. And let's consider the following probability mass function. P0, P1, P2, P3 to be 0.05, 0.05, 0.5, and 0.4. So this illustrates, one thing that this illustrates is that the probabilities don't have to be in any particular order. Here they're not ordered in increasing order like they were before. And let's encode the sequence x1 up to x4, which is 2320. So this is our sequence to be encoded. And now we're going to do a similar thing to before. Let me squeeze that up to the top so we have lots of room to draw. And let's do our interval from 0 to 1. So this is going to be very reminiscent. Just like before, we're going to start out over here and subdivide this guy. This is 0, 1, and subdivide according to this p right here. So we have a little tiny 0.05 part, a 0.05 part, we have a point, let's see, is that about, yeah, that looks about right. We have a 0.5 part and a 0.4 part. So here, this first little chunk is P0, height P0, height P1 for the next chunk. This is P2 and P3, just like before. And let's label these. So this is 0 chunk, 1 chunk, 2 chunk, 3 chunk. Very good. And now the first symbol to encode is a 2. So we focus on the 2 chunk, just like that. And we subdivide this guy. We have a 0.05, a 0.05, a 0.5, and a 0.4. So this is 2, 0, 2, 1, 2, 2, 2, 3. And again, you know, the height of this is P2, P0. This is P2, P0, P2, P1 for this one. This one is P2, P2. This one right here. I think you're getting the point. Boom, boom. And this one is P2, P3. And our second symbol to encode is a 3. So we focus on the 2, 3 chunk. Once again, we subdivide a 0.05, a 0.05, a 0.5, and a 0.4. And so this is, I don't know if you can read that, 2, 3, 0, 2, 3, 1, 2, 3, 2, 2, 2, 3, 3. This one is the one we're going to be interested in, and it's P2. P3, P2 is its height. And we were interested in that because I knew that our third symbol was going to be a 2. So we, once more, in just the same way, once more, we subdivide this dude. And we get a little tiny bit here, a little tiny bit here, a bigger one there, and another one. So this is 2, 3, 2, 2, 2, 3, 2, 3. This one, the lowermost one, is 2, 3, 2, 0, and the second one was this one was 2, 3, 2, 1. And our last symbol to encode is a 0. So we will choose the 2, 3, 2, 0 chunk. So let's write down, let's highlight that guy. A little sliver of a chunk right there. This guy. And let's draw it back over here. So this is something like this. So this is our point. This is our A. This is our B. We'll see how well my drawing was here, how to scale things were. Okay, so this is A, and this is B. The lower one is A, the upper one is B. So what is this interval from A to B? Well, let's do things, let's go ahead and compute this just like before. A to B is what? In order to compute this, let's actually, it'll be handy, it'll make life easier, if we define these numbers C corresponding to P, and it's going to be the sum, it's sort of the CDF. We're going to sum up the P's that come before that given C. So so CI is going to be the sum of P0, P1 up to Pi minus 1. So this is going to be 0, the sum up to P's of the P's up to but not including this one. And this is going to be 0.05. It's just this one. The third one is going to be the sum of the first 2. So that's 0.1. And the fourth one is the sum of the first 3 P's. So that's 0.6. So why is this useful? Because if you look down here on our diagram, what is this number? This is 0.05 right here, which is just, so well, the first one, the lowest number, 0, is of course C0. So this is C0. C1 is 0.05, right? That's C1. C2 is this guy. It's 0.1. C3 is this guy. C3 is 0.6. 0.05 plus 0.05 plus 0.5. And here's why that's going to be useful, because to compute A, what do we need? So A is, let's see. A is, well, let's see. We have to go up here. So if we think about climbing the staircase to get up to A, we have to add C2. So we go up to C2, and then we have to add this part. So let's start writing down what we have. We have C2 plus, what is this part right here? This is the sum of the 2, 0, 2, 1, and 2, 2 chunks. So that's summing up P2 times P0 plus P2, P1 plus P2, P2, which is P2 times the sum of these three, P0, P1, P2. And that is just C3, right? So this height of this chunk right here is P2, C3. And now we continue climbing the staircase, and we have to do just one more step, which is the last step is the sum of 230 and the 231 chunks, which is just, so that's just P, what is it? P2, P3. P2, P3 is a common factor in all of these heights of these chunks, times the sum P0 plus P1, which is C2. Okay, so what are these guys? So for this example, I worked everything out. I'm not going to make you watch me do it by hand. This one, it turns out, if you calculate this, it's 0.42. You know, plug in these numbers here into this expression, and that's what you get. So what is B? Well, B is A plus the height of the last chunk, right? It's always going to be A plus the height of that last chunk. And what is the height of that last chunk? Well, let's see. The 232 chunk had height P2, P3, P2. And so this last one is just going to have height P2. So this height right here is P2, P3, P2, P0, which is just exactly the product of the probabilities for the sequence we were encoding. And that's no coincidence. That will always be the case. If you think about it for a moment, that's always going to be the case. You're always going to have the product of the height of the first chunk times the height of the, it's the probability of the second chunk, and so forth. So what is this? PA plus P2, P3, P2, P0 is what? Let's see. I worked it out. So this number is going to be, this is going to be 0.005, and you get 0.425 for B. So our interval from A to B is the nice interval 0.42 up to 0.425, and let's circle that. No, change color on me. My pen sometimes changes color on me. Okay. There we go. So that was the conceptual first part in the process. The reason why I keep saying the conceptual first part and the conceptual second part is because when you actually implement this in the finite precision algorithm, the two parts are going to be interleaved. They're going to be sort of combined. And so it doesn't really make sense to sort of refer to this as the first part and that this is the second part. But conceptually, while we're doing the infinite precision algorithm is much easier to get your head wrapped around, and the finite precision algorithm works in basically the same way. So the second part, let me get rid of this C here, make a little bit more room for our, let me get rid of this to make a little more room. Cut. cut, paste, make room for our other part of the diagram. Thank you for... Okay, that was our C. Now, for the second part of the diagram, what do we have? We do the binary thing. So over here, we're going to have this binary splits. And looks like I'm definitely gonna run off the page here, so this is gonna be a nice... And we have a really tiny interval to hit, so you can see that this is gonna be a longer sequence. So 0 up to 1, and now we do binary splits. So what is this gonna look like? So let's say, so we do a binary split, so it's maybe around somewhere around there. And we'll do the same thing. Let's label these 0, 1, and it's in, we need to get something in this interval, so we divide the 0 part. Maybe I should actually, let me make this a little bit tighter. All right, so now we have somewhere around there, and this is our 0 chunk, our 1 chunk. This is 0 up to 1, and we're in the 0 part, so we divide this guy. So we get something like that. This is 0, 0, 0, 1. And then we have what? We have 0, 1, 0, and we have 0, 1, 1, 1, and then we, so let's compute these guys so we can see where we stand. So 0.01 binary is a quarter, 0.25. This is a half. This is 0.5. 0.11, or rather 0.011 is what? This is a quarter plus an eighth is 0.3, so 0.1 to 0.375. We're trying to get within 42 to 425, so we're definitely in the 011 part. All right, so we're gonna do this guy again. What do we get? So if we split this right around there, so this is 0110, 0111, and now this 0111 is what? It's 0.375 plus a 16th. And let me just write down what these are, so you can compute these if you want, but rather than make you watch me calculate them, 0.0111 is roughly 0.4375, which is still above our 0.425, so we have to do this guy again. And what do we get? So let's see. So here we have 01100, 01101, 01101 is roughly 0.406. 406 is less than 42, so we keep going until we get in there. So let me make it a little bigger. 01101, 01101. And now, let's see, so let's make a little room. What is 011011? It is roughly 0.42, well, you know, so it's exactly 0.4219. And 0.4219 is in our interval. It is in 0.42 to 0.425. So we have a number in there. And now so let's decide, do we want to go above or do we want to go below? So let's see. So 0.4219 is certainly closer to 0.42 than it is to 0.425. So we're going to go in the upper half yet again. You won't always go in the upper half. Sometimes you'll end up in the lower half. Okay, and now I'm really running out of drawing. I can't write the numbers in here anymore. But you're going to get, so this one's going to be 0.01101110, and I think you get the 0.01101111, and you have to keep going, so I won't write down all the things, but if you divide this guy once more, then what you end up with, that last number there is, so this one's going to be 011011100. The top one is going to be 011011101, and that binary number 011, oh, excuse me, that's not quite right. We have to go one more, even further. So that one's that one, and then yet again, if you divide it once more time, then you get the lower guy is 011011000. The upper one is of course, 011011001, and the corresponding binary number 0.01101101 is roughly point what is it 0.424, which is in our interval. It's just inside the top part. 0.424 is in here. So finally, after the last subdivision there, you end up with that little tiny interval. And sorry that it's too small to draw, but I wanted to give you a non-trivial example of a sequence that was of sort of non-trivial length. So the bottom part of that last little, that last chunk has label 011011000, and its chunk is completely contained in here because this number, so it's the interval from, what is it? It was this one, 0.4219 up to 0.424, which is contained in this interval from A to B, is contained in 0.42 up to 0.425. So we have a winner. So this guy right here, let's draw it. So 011011000 is our winner. Boom, boom, boom. So let's draw that back over here. All the way back. And miraculously, it is pretty close to lining up with our actual A to B. So we encode this. So this chunk has this interval, this little tiny interval right here, and it's this one, and it's contained in our original A to B. So we encode. So we are done. We encode 2320 as what is it? Oh, sorry, I should write it down here. 011011000. 01100. Oh, and that is it. All right, so that was another example of the basic idea of arithmetic coding, again in the infinite precision case. So we're assuming that we have infinite precision that we can compute with, but obviously, even here my pen ran out of precision. So clearly on a computer you're going to have to do something different, but this is the basic idea. And I'd like to mention one thing which we can observe at this point, which is pretty clear, and we saw it in this case, which is that in general the length of the interval that you end up with here, this interval from A to B, is always going to be the product of the probabilities of the sequences of the symbols in the sequence that you're encoding. So it always happens. So we have the following note, which is very important later on when we look at the properties of arithmetic coding in terms of how good of compression we achieve. So the length of interval from A to B is always, well, of course it's always B minus A, but B minus A is always going to be the product px1 times px2 up to pxk times p0. So if 0 is, if our sequence is of length k plus 1, then it's the product of all these probabilities. And the reason for that is just because, right? It's just because that's exactly what we were doing in the subdivision process. That was how we defined the lengths of the subintervals, was that they were the products of those probabilities up to that point. It was P2, P0 times P2, P1 times P2, P2 times, it was P2, P0 and P2, P1 and P2, 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 P3, and so forth. So this is always going to be the case. This is a very important observation. This is what gives arithmetic coding its nice compression properties. Okay, so hopefully these two examples, example 1 and 2, give you a sense of the basic idea behind arithmetic coding. And hopefully it was clear, even though in this one I ran out of drawing precision, it was clear what was going on. And I think it is in the infinite precision case. It's conceptually, once you sort of see the picture and you see what's going on here with this subdivision and subdivision over here, I think it's pretty conceptually, it's not too hard, it's not too bad to sort of get your head wrapped around what's going on.